Welcome to another video for Calculus 1, no? And yeah, this video will be talking about another method in solving limit functions in that leads you to indeterminate forms, or that leads you to indeterminate values. So as we recall, no, from the previous lectures in solving limit functions, no, it gives you many ways, no. Let's say that you need to simplify the equation first before you plug in the value of x, no, the value of x as you approach to a certain value, no. Such a way you may be certain that it may, if you don't have any choice with the equation, and you may conclude that the value is does not exist, or yeah, exists or does not exist. If you lead to an indeterminate value, eh, you concluded that the value does not exist, right? But in some other ways, indeterminate forms are very, yeah, these are equations that might confusing to you, but in some other ways you could solve it, no, in other methods, such as this hospital rule, no. um when you take the limit of an indeterminate form as x approaches to something, let's say you solve it, when you plug in it to the value of x, you concluded this indeterminate value, and you look again to the value of the equation, to the form of equation, and then you cannot simplify because it's complicated. And when you simplify it, it still give you an indeterminate value. So what happens now, it's uh from before, is since you have no other choice, you may concluded that the given equation does not exist, or the given statement does not exist. So anyway, when maybe I will introduce this hospital rule way back then, you may not understand this because um the way that the hospital rule will do its solution is that you need to learn about the differentiation formula first, apply this one to the equation, and gives you another way to simplify the equation, and maybe it will not lead you to a indeterminate value or infinity, or that gives you the idea that the statement exists, right? So yeah, so before we go to the methods itself, let's have a recall back, no, to taking the limits of a indeterminate form, no. One of the functions, or one of the example given by the book of Stewart, is that you have here the limit. So the limit of um x squared minus x to the power of x squared minus 1, and your x is approaching to 1, right? So this give you an indeterminate value because look here at the denominator. If you plug in directly the value of 1 to the equation of the denominator, this is a rational equation. So this is 1 squared minus 1. And it gives you 0. And a fraction with a value with a denominator of 0 gives you infinity, and therefore the equation does not exist. And way back then, one of the solutions that you could use here is to simplify this rational equation, right? So this is the limits of the given equation as x approaches to 1. Um the common multiple of the numerator is x, no, right? And you could factor it out as x times x minus 1, right? And denominator itself is a perfect square, and so you could factor it out also as x minus 1 and x plus 1, right? So you could cancel out x minus 1. See, you could simplify this. So what happens now, what remains of our limit function is that this limit a as x approaches to 1, and this is x all over x plus 1. And so when you directly plug in the value of 1 to the given simplified equation, you know that it will not lead you to an indeterminate value. So you could plug in this directly with the given value of x, which is 1. No, this is 1 and 1 plus 1. And that gives you 1/2, right? Okay. L'Hospital rule. To perform L'Hospital rule, let's say commonly you have a rational fraction, no? Rational equation, rather, and you have uh let's say x approaches to a certain value, let's say a, and you have f of x all over g of x. Performing a L'Hospital rule here, you need to at least perform differentiation to either of, let's say your variable here is x, so you differentiate um the the numerator or the function of x as the numerator of the rational equation all over the different differentiation of the denominator, no, the equation of the denominator, which is the g of x. And then you perform here um uh yeah, you perform uh the value of uh you plug in here directly the value of your x here, which is a, no? And you can get the value. So let's try that one into our given example here. Let's say I would just you could directly write the given differentiation, no? But for the sake of the others who may be confused, I will be writing it step by step. Okay, so again, the limit is x squared minus x all over x squared minus 1 as x approaches to 1. And you know that you could not plug in directly the value of x here because it will give you an indeterminate value. By the L'Hospital rule, you differentiate, right? The numerator and the denominator separately. I am writing this with the correct notation because we are using the variable of x here, and so you should be deriving it with respect to x, not by any variable. Okay, so this is equivalent to limit of as your x approaches to 1, differentiation of x squared, that is 2x and minus 1, and this is 2x. I don't know. Yeah, 2x. Okay, so yeah, and that gives you what? And that gives you, you could now directly employ this. So that is 1, no, 2 times 1 minus 1 all over 2 times 1, and that gives you, yeah, 2 minus 1 all over 2, or that is 1/2. See, you could have the same value as what you could get on your first solution. Any of these two are considered as mathematically correct. So you could have this both as your solution, no? Let's just say you are using L'Hospital rule in your second solution. Okay. So that is basically it, no? That is just how you perform the L'Hospital rule with the indeterminate forms. So what other else that you could consider is there might be some of uh indeterminate forms that you really cannot use, no, with L'Hospital rule, so be careful. And so maybe you could do two options. So maybe you use L'Hospital rule first and you end up with indeterminate value. And then when you use the other method, like say simplification or using some identities to plug in or to simplify the given equation, and it will lead you to maybe a concrete value or a determinate value, then use that method and not the L'Hospital rule on the other way around, right? So yeah, let's have more example. No? Okay, one of the example here is limit as your x approaches to 1, and the equation, the rational equation is ln x, or the natural logarithm of x all over x minus 1. Now, some of the cases is that your given equation could not really simplified, no? Here, in the first thing that you notice is that when you plug in the value of x, which is 1, you get a determinate value. So meaning the equation or the rational equation itself is an indeterminate form. No. But you could have, you could, you don't have much choices, no? Um, you cannot perform any simplification with this equation, but rather, you will just apply the L'Hospital rule directly with this one. So again, I will take one by one or step by step of applying L'Hospital rule here. So copy the limit and derive the numerator with respect to x. That is ln x over d over dx times x minus 1. So this is equivalent to limits as your x approaches to 1, no? And that is this is 1 over x all over 1, right? So yeah, I think you could probably uh plug in it. No, this is 1 over 1 all over 1, and so this is equivalent to 1, right? So the value of the limit of ln x as ln x all over x minus 1 as your x approaches to 1 is equals to 1. Okay, you're happy because you could get the determinate value of the equation, given that you could not really simplify the given equation, right? So, okay, let's have other example. So yeah, we have the second example, which is limit of the exponential of x as your, I know, exponential of x all over x squared as your x approaches to infinity. Okay. Now, where could you possibly say that the given statement is indeterminate value? No, you take steps. So when you plug in it to the numerator, that is e to the power infinity, this gives you infinity, right? And for, yeah, for infinity to infinity squared, that's still equivalent to infinity. And so rather, this gives you the idea that it is still a, yeah, this kind of equation does not exist and it will lead you to a determinate value, diba? So could you simplify it using your algebra, no? The based on your algebra, maybe you could not simplify it, And so we don't have any choice here but to apply L'Hospital rule, no? So this, I will just directly write the equivalent of the derivatives. No, I will not write this one. So this is equivalent to, yeah, the derivative of exponential x is still exponential x. The derivative of the exponential, no, the x squared is 2x. And so if you plug in here the Euler number, or e raised to infinity, it's still infinity. And 2 times infinity, it's still infinity. So this will give you the idea that this kind of statement does not exist, and it will lead you to infinity, right? Okay. So yeah, sometimes you need to really justify the statement, no, to really have your conclusion. Okay, let's have more example. Right? Okay, let's have this. So limits as your x approaches to infinity, and the rational equation is ln x all over the cube root of x. So we'll just directly derive this one because you did not simplify this using your algebra skills. So limits as your x approaches to infinity, this is 1 over x, and this give you 1/3 of the, yeah, x to the power of negative 2/3, right? So that is 1/3 of x to 1/3 minus 3 over 3 as 1. So that is 1/3 x to the negative 2/3, right? Okay, so what can you, how can you simplify this? So this is, okay, so you could combine, the value of x here. So we have a common value. So this is equivalent to 3 all over x, no? 1 minus 2/3. And so this is equivalent to, I know we forgot to put the limits. So limits to x approaching to infinity, and gives you 3 all over x, 1 minus 2/3, or oh, 3 over 3 minus 2/3, and that gives you 1/3, right? So this is, okay, this is limits as your x approaches to infinity. So this is 3 all over uh 3 over the cube root of x, right? So when you plug in the value here, so this is equivalent to 3, um 3 of infinity, it's still infinity. So this is 3, a definitive value over infinity. And recall back to the idea that 1 over 0 is infinity, right? Yeah. Yeah, 1 over 0 is infinity. And so any number divided by 0 is equivalent to infinity. if you derive this one, that would be 1 over infinity, which is equals to 0. And so any number divided by infinity would be equals to 0. And that's what's happened here. So that is equivalent to 0. So the limits as x approaches to infinity of ln x all over the cube root of x is equivalent to 0 here. Okay. More examples. So another example would be limits as your x approaches to 0. So the rational equation here is tangent x minus x all over, yeah, x cubed. Okay. So the idea here, since you have a lone denominator x cubed that is 0, when you plug in the value of x here, that is 0, and it will lead you to the determinate value. So yeah, could you simplify it? Because of the tangent, you may stuck in with this equation, but rather apply L'Hospital rule. So limits as x approaches to 0. This gives you tangent x, which is secant squared x minus 1 all over 3x squared. The way that you differentiate this is very much different, no? Because when you differentiate a rational equation rather, you may be using division rule, but since we are applying the notation of limits, this is just how the L'Hospital rule uh be applied, no, with the limit functions. So these are the steps and we should need to follow. So, anyway, um so since you are simplifying it already, that is secant squared x minus 1 all over uh 3x squared, right? So when you recall that, when you applied or you plug in the value of 0 to the value of your x on the equation, you still ended up with indeterminate value, right? So since it's still, then what you will be able to do, you may be able to use another L'Hospital rule. It still be applicable because the equivalent of this is still applicable when you do the L'Hospital rule twice, right? So I will be applying L'Hospital rule here twice. So secant squared x, this is um this is uh yeah, this is secant squared, right? So yeah, secant squared is secant x quantity squared, and so the differentiation of this is 2 secant x times the secant x and the tangent x, now by chain rule, right? So this is equivalent to 2 secant squared x and tangent x. You put it right here, so that is 2 secant squared x times the tangent x divided by uh 3x squared, that is 6x. So Okay, how about this? So, could you simply plug in the value of 0 here to the equation? So, when you plug in the value of uh, 0 to second squared x, this will be equivalent to 1, right? So, uh, yeah. And yeah, so that is 1. And what's left here is, let's just show the solution, or simply the solutions. So when you plug in the value of your second here, uh, so this is simply 1 over cosine squared of 0, which is equivalent to 1. No? So this is 2, no? 2 times 1, which is equivalent to 2, divided by 6, that is 1/3. So by loss of limits, you could take that out. So that is 1/3, no? And copy again the limits as x approaches 0. So yeah, so that leaves you tangent x all over x. And yeah, you could not deliberate this because it still leads you to an indeterminate value. So that gives you another um execution of the L'Hospital rule. So maybe for the last time. So this would be second squared x all over 1, no? Or just second squared alone. And second squared by limits, as we perform, right, this is a 1, right? So this is just equivalent to 1/3. So that is a value. Let's have another example. So the other example is limits as your x is approaching to uh, negative values of pi. So that is pi to negative. Sine of x to all over 1 minus cosine of uh, x. Right. So what could we apply here? Yeah. Sine sine uh sine of pi, I think that is 0, right? Am I correct? Or I think sine of pi is 0, right? And cosine of pi to the negative is -1. Yeah, -1. But anyway, let's apply the L'Hospital rule here first. And this gives you limits as x approaches to pi to the negative. And this is cosine of x. And this is 1 plus sine of x. Right? So this gives you, I don't know, just sine of x there. Because derivative of 1 is 0. So uh when you plug in the value of pi to the negative here, sine of pi to the negative, this gives you infinity because sine pi is 0 and any value divided by 0 is infinity. And so you will lead with a determinate value. But there's a but here. Notice that when you plug in the value of pi when you are not applying L'Hospital rule, you may have a determinate value. solutions. This is sine of pi to the negative all over 1 minus cosine of pi to the negative. So that gives you 0, and this gives you 1 minus negative 1, or 0 all over 2, and that still gives you 0. And this is a determinate value. This is a determinate value rather than infinity. So this solution is the go-to rather than the L'Hospital rule. So be careful for which you may be end up with determinate value instead if you are using L'Hospital rule, right? Okay. So that's maybe the disadvantage of this. No? But at least you have the more methods that you could use, the more reasons that you could get a real determinate value of the indeterminate forms, right? Okay. Um what are other indeterminate forms, no? Um uh you may have um indeterminate forms which for which in some cases such as like this, no? Let's have an example of this one. Okay. This one. Why it's indeterminate form? Because ln is 0, we could not have a value of this. This is indeterminate form. If you type it in the calculator, it will lead you to a math error. And so this is indeterminate. And when you apply maybe the differentiation here, maybe use product rule, you may still end up with indeterminate because it leads you to ln x also, no? You still leads with ln x, but yeah, and still lead you to indeterminate value. So one way to execute this is translate this kind of situation or this kind of equation to become a rational equation, no? Just like what we are used in solving from the previous examples, no? All of the examples are in a rational equation. So what we could do with this one is translate this one. This is equivalent to limits as x approaches to 0 positive. This is ln x all over 1 over x. And 1 over x, when you reciprocate here, this one, and it still gives you the exact value. So this is still mathematically correct. And when you perform this, this is limits as x approaches to 0 positive. And this is 1 over x all over, yeah, negative of 1 over x squared, right? So yeah, simplifying, uh, this will give you negative value. Now this one can be reciprocated, and it will give you negative x, right? And so when you plug in the value of 0 here, it still gives you the 0 value here. Okay, so that is the value in which if you directly solve this, it will give you indeterminate values. So, yeah. Okay. What other forms of indeterminate functions? Let's say when your variable x, when your x is approaching to infinity, some of the equations may lead to indeterminate values, such as this one. So limits of x as your x, limits of um, x times exponential of x as your x approaches to negative infinity, right? Go back. Ano na may parenthesis? Okay. Negative infinity. So, negative e to the raise of negative infinity is 1 all over, um, yeah, e to the power of infinity, and this is 1 all over infinity. So, this may be 0, no? And, yeah, this may be 0, and x is just infinity. Infinity is infinity. So, yeah, you're not sure when you plug in the values here. What you could do is that, yeah, like what we transform with the previous example, no? Let it be limits as x approaches to negative infinity, and yeah, we could use x to the power of 1 all over exponential of negative x. So this is still the same with this one. Or since this is 1 all over exponential of x, this is e to the power of negative x here. So when you apply L'Hospital rule, so this is equivalent to 1 all over, yeah, um yeah, negative of negative, a negative of exponential of negative x, no? And this is 1 all over negative of exponential of positive infinity, because, right, yeah, positive infinity, because um so, and still gives you infinity, and so this is equivalent to 0, no? from from 1 over 0 is equals to infinity, and so 1 all over infinity, that is equivalent to 0. So this is equivalent to 0. So could we have more examples? Okay, how about this one? So limits as x approaches to um pi over 2 to the negative side, no? Of the equation secant x minus tangent x. Okay, so in this situation, since it's trigonometric, so we need to apply the identities, no? Looking back, secant of x is 1 over cosine of x. This is sine over cosine. And when you apply pi over 2, cosine of pi over 2, or cosine of 90 degrees, I think, right? Cosine of 90 degrees is 0. So this is 1 over 0, and it will lead you to indeterminate value, or infinity, right? Still, this is, yeah, this is 1 all over 0, no? Sine of pi over 2 is 1. Cosine pi over 2 is 0. This will give you infinity. Applying L'Hospital rule, yeah, we could use that, but we could use a little bit simplification first, no? So this is equivalent to limits as x approaches to pi over 2 to the negative, no? Again, this is 1 over cosine of x minus sine of x all over cosine of x. So this is limits of x approaching to pi over 2, right? We could combine this one. So common ang denominator. So this 1 minus sine of x. Okay. Here we could possibly use L'Hospital rule. So this is limits as x approaches to pi over 2. This is negative of cosine x all over negative sine of x. So you negative over negative, that is positive. And that gives you limits as x approaches to pi over 2 negative cosine of x over sine of x. So this is 0 over 1 and this is 0. So what else? We're down to last two example here. But I still require you to study about the subchapter, no? I'm just giving you the idea. Maybe the texts in the PDF might be confusing, and I'm just giving you the explanation out of it. No? So let's have another example. Last two. No? So this is limits as your x approaches to 0. And we have here 1 plus sine 4x to the power of cotangent x. Reminding that cotangent x is cosine x over sine x, right? And our value of x here is 0. So this is cosine 0 all over sine 0. Cosine 0 is 0. I know, cosine 0 is 1, while sine 0 is 0. So this will lead you to infinity, and exponent to infinity is still infinity. So this gives you an indeterminate value. So how could we pull up this one? Now this way we need some special simplification. This is what you call the indeterminate powers. So how? So we let the given equation as y, so this is y, as 1 plus sine 4x to the power of cotangent x. Like what I've said from the previous videos, no, one of way to simplify exponential functions is just using logarithmic values, logarithmic functions rather. So we will ln both side, ln y and ln of 1 plus sine 4x to the power of cotangent. Now by the power of or by the definition or by the law of exponential function, so this is equivalent to cotangent x times ln of 1 plus sine 4x. Okay, happens now. So yeah, so what happens now is that cotangent is also uh 1 over tangent x. So ln y is ln of 1 plus sine 4x all over the tangent x, right? And yeah, by L'Hospital rule, we could yeah, the idea here is we could still apply L'Hospital rule. And so by doing limits a ln by both sides, we could also possibly use limits of both sides that's still applicable. So we just follow what is the limits here, limits of x approaches to 0. So we did it right here. So approaches to 0 positive ln of y, limits of approaches to 0 ln of 1 plus sine 4x all over tangent x. So by L'Hospital rule, so ln of derivative of ln of 1 plus sine 4x is 1 all over 1 plus sine 4x times 0 plus sine 4x, which is cosine 4x times 4, right? All over secant squared x. So this is limits as x approaches to 0 positive. So this is 4 cosine 4x all over 1 plus sine 4x. And much longer fraction line, no, to this just signify the denominator and the numerator. This one. So could we apply 0 here? Yeah, maybe. So I could change this as 1 over cosine squared of x. So this is 4 cosine of 4 times 0 all over 1 plus sine of 4 times 0 all over 1 all over cosine squared of 4 times 0. So this is, wala ning itarong ha. This should be much shorter. So this is equivalent to 4 times cosine 4 of 0. This is 4 times 1 all over 1 plus 0. Sine of 4 0 is sine 0, and so it's 0. So this is 1 all over cosine squared of 4 0. That is still 1. No? So this is 4 over 1 all over 1. And that is 4. Okay? So last example. What other else that it may lead us to infinity? Okay. To indeterminate functions. So we have here yeah. Let's have another sheet here. So that is limits as x approaches to 0, and the equation is x to the power of x. So just like what we use here, what we use from the previous notations. I don't know, a different day. Okay, remember that e to the power of ln x is just equivalent to x, right? And ln e to the power ln of e is 1, right? Yeah. So anyway, what we could use here is this kind of statement. Either way, this is e to the power of ln x. This could be no, to the power of x also. This is also e to the power of x ln x. So we will apply it here. So that is lm no, limits of x approaches to 0, um, e to the power of x ln x. So this is e 0 times ln of 0. This might be leading to indeterminate function, but this 0 factor saves the day, because any value that multiplied by 0 is 0. So this is uh, equivalent to e to the power of 0, and any value raised to the exponent to 0, this is equivalent to 1. So that is equivalent to 1. Yep. So far that's all. No, that's all of the equation for the indeterminate forms. So kindly answer the given activity for this one. So Merry Christmas, and see you by, yeah, next meeting, which is maybe next year. Thank you and goodbye.